Hey guys, so today we're going to be talking about kinetics. What is kinetics? Kinetics, what does it sound like? Kinetics sounds like something's moving, something's going, something's progressing forward. Usually when you think of kinetics, you think of things zipping around all over the place. In this case, when we're talking about kinetics, we're talking about the speed of the reaction. Now, most of the reactions we've done so far have happened pretty quickly. They've gone pretty much instantaneously, or if not instantaneously, so quickly that we can watch the entire reaction in a moment or two, just a few seconds. But that's not what most reactions do. There's a lot of reactions out there that happen very, very slowly. Um, for example, there's the decomposition of hydrogen peroxide. That's something that happens all the time. When you have a bottle of hydrogen peroxide, it'll decompose to oxygen and water without any help of any kind. Usually, whenever we want to see it go faster, we have to add a little something to it called a catalyst, but we'll get into catalysts later to make the reaction go faster. We're going to speed it up, the reaction. So reactions can be slow, reactions can be fast. For example, the potassium permanganate reaction that we did in our previous lab, that happened pretty much instantaneously. It's almost like magic. But a lot of times, some reactions happen a little bit slower. For example, one great one is diamonds, carbon diamond. So carbon, whenever it's in its diamond form, will just naturally turn into graphite, like pencil lead. It is constantly doing that, but it's super, super slow, on the order of like 10,000 years slow. So don't worry, that diamond ring or diamond earring you have isn't really going anywhere, at least not for the next 10,000 years. But when they say diamonds are forever, that's a lie. Diamonds are for like the next 10,000 years. So, like I said, it's super, super slow. There's plenty of reactions out there that are really slow. So, what we're going to be talking about today is kind of measuring how quick those reactions are, something called the rate of the reaction. Now, when we talk about rate of the reaction, we're going to talk about the change in the concentration over the change in time. Now, most of the time, we're going to be talking in this section. We're going to be referring to molar most of the time, the concentration. So, change in concentration over the change in time. So, if we wanted to look at this, this very simple reaction, A goes to B, A to B. All right. What we can do is look at our change in concentration and our change in time. So T0, T equals 2. So this is 2 seconds passing, and we are losing a little bit of our reactant, which makes sense. We're kind of using up the reactant, and we are gaining a little bit of this product. So what we can do is, what's the change in this concentration? So one thing we want to think about here, you can think of rates as speed. So when you think about speed, you think of miles per hour, some sort of distance, something over time, per hour. Here we're going to be talking about molarity, molar per second. Okay, so here, first thing we need to do is figure out what is the change in A and what is the change in B. And remember, anytime you're talking about change, you always think about final minus initial. So what's the final minus initial here? So we can get out our good old calculator and figure out minus 1.00. And we see that we have a change of negative 0.02. And then what's the change in time? 2 minus 0 is 2. So if we look at that, we will see that our rate of A disappearing, or the rate of A, is negative 0.01 molar per second. So this is kind of how quickly A is disappearing. Now, when we talk about rates, this is just a convention thing. We never talk about negative rates. Kind of like you don't have a negative speed. So you can't. There's no negative speed. We always think about positive speeds. So here, one thing you have to remember is that when you're talking about reactants that are disappearing, you need to flip the sign to make this a positive. So we talk about a positive rate of disappearance for reactants. It makes sense. Reactants, you can think they're getting used up. Products, on the other hand, you don't have to flip the sign because these things are appearing. And we just say the rate of appearance, the rate of disappearance. We can do the same thing here. This is the exact same calculation. And so it's going to be 0.01 molar per second. So this is going to be how we're going to go through and calculate any type of rate of reaction. Boop, boop. Okay, so again, positive rates only. Always remember that reactants are going to be decreasing, products will always be increasing, and we always consider rates to be positive. So just always remember that. All right, so let's go for a little bit more complex example here. This is going to be something you're going to see quite often. You see concentration on this side, time over here, and you're going to see this chart, okay? And you can go through and see that from 300 to 400, this time change is going to be 100 seconds, and we can calculate what each of these things are. Let me kind of blow this up for you a little bit. And we can go through and calculate that. So we have a change in the concentration and a change in time. So if we go through and look for NO2, we can calculate this. You can find the change by looking here at here to 0.2 and calculate it. They've already done the calculation for you right here. But if we wanted to go through and calculate the rate of this guy, let's get our calculator out again. It's going to be 0.0037 molar. That's going to be the change in NO2 divided by 100 seconds. And here we have our rate. Now, each of these are going to be 100 seconds, so these are going to be pretty much the same thing. And now, here you can see something kind of interesting, okay? Going back to this balanced equation up here, we see that we have 2 dinitrogen pentaoxide going to 4 nitrogen dioxide plus 1 oxygen, O2, okay? And let's take a look at what's happening here, okay? Now, NO2 was 4 to 1 with oxygen, right? And let's bring out a little calculator again. And we can say 0.0037 divided by 4. And looky there, 0.0009, which is the same molarity, change in molarity for oxygen. Okay. Same thing. Let's check it with the N2O5, the dinitrogen pentaoxide. We have 2 to 1. So if I go through and check that out, and sure enough, there it is. So that is going to be something that we can do. We can use that balanced equation, this balanced ratio, to figure out in between these times, we're going to have a similar amount of reactant being used, product being used, so on and so forth, which makes sense. If it takes 2 N2O5s to make 1 O2, then the change in concentrations should be that same type of ratio. So that's going to be something that is true that we can do. We can use stoichiometry here to figure out rates as long as it's in the same time frame. 300 to 400. Okay. All right. So we can do that. We can use stoichiometry. So as long as you know the rate of one, you can figure out the rate of everything else. In some more complicated things, where there is no coefficient of 1, there is no 1. Like here we have O2, there's a 1 there, an understood 1. You can just go through and say, 1 over 2 for this, 1 over 4 for this, 1 over 1 for O2. So if I wanted to write what if I said, okay, let me see here. Let's say we had something absolutely bonkers, like 2AB2 goes to 2A 2B squared. I don't know. Some sort of thing where you don't have a 1 coefficient. Each of these can be described as the change in AB2 over the change in time, but the thing you have to do is it is 1/2 this change in time. And since this is a reactant, it's going to be negative 1/2 AB2 over change in time. All right. So there's that. This is just a quick and easy way of not quick. This is a way that you can go through and calculate the rate of reactions on each of these things. All right, so far we've been talking about molarity per second. That's going to be what we're going to be using most of the time, but you can also use atmosphere per second or liters per second or precipitates. You can use grams per second. Any of these. Basically, if you can go from moles to the thing, then it's fair game. Yeah. Yep. Okay. All right. So a little bit of practice problem. Let's consider this reaction here. In a certain experiment, over a certain time period, we have this many moles of pH3 consumed in a 2.0 liter container for each second of the reaction. What are the rates of production for P4 and H2? All right, so this is going to be pretty straightforward. So again, this is just a stoichiometry problem. So here we have 0.048 moles of pH3. And since this is for each second, we don't have to worry about like adding time to this yet. This is just a straight stoich problem. We know there's going to be 4 pH3 for every 1 P4. So it's this divided by 4. And we can grab our calculator and figure that out. Okay, so 0.012 moles per second of P4 being created. Okay. And same thing for this. When we talk about H2, we can just swap this guy in here. And do that. 48 times 6 divided by 4. And they are going to be 0.072 moles of hydrogen gas produced per second. Here we go. There is that. We can go through what is the relationship between the rate of production of ammonia and the rate of consumption of hydrogen. So we can just look through here. What is this this relationship going to be? And again, it's just kind of a 2 to 3 relationship, 2 to 3 rate of production. For every whatever the rate of production of ammonia is, then hydrogen is going to be 3 over 2 that. Okay. All right. That's that. I'll see you guys later.